Video help for problem 11.10. See the written homework advice. There's some extra, little formulas and things connected there that I won't repeat here. But I just want to tell the story. We're looking at the Fourier transform of the exponential function. And actually think of it this way. Think of looking in time as at the radiation from an excited atom, and you'll see that it decays exponentially. And of course, you might just want to think about time from t equals 0 to the decay. But actually, what this Fourier transform that we're looking at, we could actually look at just half of this and still see that we get a Lorentzian form. What we do here is say that when you have an exponential, decaying in both directions, and by the way, when you look at the derivatives, you see that you have this cusp then, because the derivative changes here. So the next derivative would give you a jump. You're just going ahead and cranking out the Fourier transform. You're going to get a Lorentzian. You just split this up. I'm always, whenever I've got absolute values, I always start, writing them down for the different regions. Positive t, negative t. Then, my exponentials are different. I split this up. See the homework advice written out. And you get a Lorentzian form. You get something over something plus another something times f squared. You get these Lorentzian shapes, and that's the shape of the spectrum, of the radiation, or of an excited atom, for example, that is often discussed. When you get done with your formula, by the way, you could put t2 equals 1 and check against our table. Well, that math was easy, just exponential integrals. In part B, if you're going to calculate the area under h of f, the area is just then the integral df h of f. This is just the limit, for a continuous function to get this area under it. And I always, I always like to see if I can do the integrals myself. I irrationally want to always figure out, can I derive the formula? You don't need to, you can just look it up. But what I do here, this is something you did in calculus. I just change variables from, rewrite changing variables and then change them. Finally, we're using x equal tangent theta. Dx is secant squared theta 1 plus tangent squared secant squared. It cancels out to get the most trivial integral. And for this guy here, you're going from minus pi over 2 to pi over 2 and so forth. Now, in C, what is cute, though, if you go back to the inverse Fourier transform, calling that the Fourier transform, you look at this. Is this related to that for some t? Well, in part D, and the thing that's neat here is that then this would be an instantaneous way to get this area just by going back to what h of t was. In part D, if you can't measure, specific values of time very easily, like for example, you can't get t equals 0, then h of 0 is not known. Well, but you did know h of f fairly decently over a range. Well,